The important physical properties of lanthanoids are: all lanthanoids are soft and silvery white metals. The hardness of these metals increases with an increase in the atomic number. They are electropositive and therefore very reactive. They rapidly tarnish in air due to the formation of an oxide coating on their surface. They are good conductors of heat and electricity. Their physical constants, like melting point and density, change gradually, except in the case of europium, ytterbium, samarium, and thulium. Many of the trivalent lanthanoid ions are colored, both in their crystalline state and in aqueous solutions. The color of these ions is directly related to the number of unpaired electrons in the 4F subshell. The absorption spectra of the compounds of trivalent lanthanoid ions show a very sharp line band in the UV visible or near-infrared region. These bands are due to internal electron transitions in the partly filled 4F shell and are called F to F transitions. Lanthanoid ions that have empty F orbitals, like trivalent lanthanum, half-filled F orbitals, like trivalent gadolinium, or completely filled 4F orbitals, like trivalent lutetium, are colorless. Due to the presence of unpaired electrons in the 4F orbitals, all lanthanoid ions show paramagnetic behavior with the exceptions of trivalent lanthanum and tetravalent cerium with F0 configuration, and divalent ytterbium and trivalent lutetium with F14 configuration. Paramagnetism is the maximum in dysprosium. The value of the first ionization energy of the lanthanoids is about 600 kilojoules per mole, and of the second ionization energy is about 1200 kilojoules per mole. These values are comparable with the values of the ionization energies of the alkaline earth metals, particularly calcium. A detailed study of the third ionization energy shows the extra stability associated with empty, half-filled, and completely filled orbitals of the F level. This is reflected by the abnormally low value of the third ionization enthalpies of lanthanum, gadolinium, and lutetium. Now, let us look at the chemical reactivity of these elements. The first few members of the lanthanoids are quite reactive and show chemical behavior similar to that of calcium. However, with an increase in the atomic number, they behave more like aluminium. The standard electrode potentials of the Ln+3 Ln couple indicate that all the lanthanides are more reactive than aluminium. Let us now look at some important reactions of these elements. These metals combine with hydrogen when heated gently in the gas and form hydrides of the type LnH2 and LnH3. On being heated, these elements combine directly with nonmetals and form carbides with carbon, nitrides with nitrogen, sulfides with sulfur, and halides with halogens. They liberate hydrogen from dilute acids. They burn in oxygen to form oxides of the type Ln2O3. They react slowly with cold water but more rapidly with hot water. And liberate hydrogen gas. The lanthanoid oxides and hydroxides are basic in nature, like alkaline earth metal oxides and hydroxides. Let us now look at the uses of lanthanoids. Lanthanoids are widely used for the production of alloy steels for pipes and plates. A well-known alloy, mish metal, which consists of 95% of a lanthanoid metal, 5% of iron and traces of sulfur, carbon, calcium and aluminium, is used in a magnesium-based alloy to produce bullets, shells and lighter flint. Mixed oxides of lanthanoids are used as catalysts in petroleum cracking. Some individual lanthanoid oxides, such as europium oxide and terbium oxide, are used to produce the red colors on television screens. The oxides of praseodymium and neodymium are used in glass, such as in television screens, to reduce glare.